Welcome friends. In this lecture on biometry, we will cover the important concepts of biometry, the axial length, the keratometry, and the A constants. So this course will give you a beginner's understanding of the world of biometry for intraocular lenses. We will divide this course into three parts. The part 1 will be about the keratometry. Part 2 will be about axial length, and part 3 will be about A constant and the A constant optimizations. So what you see in this picture is a model eye, and one of the most famous model eyes was the Gullstrand eye. The Gullstrand eye gives us the refractive index and the radius of curvature of the cornea and the lens. It also gives us the refractive index of the other mediums of the eye, for example, the aqueous humor, the vitreous humor. Well, all formulas will need a basic information of the patient, that is keratometry, axial length, and A constant. And the basis of these indices that has been provided by the Gullstrand eye or other model eyes, they will give us and calculate and give us the IOL power. More modern formulas like the Barrett Universal 2 and other formulas like the Holladay 2, they will need more data of the patient. For example, in addition to keratometry, axial length, and A constant, they will also require other important informations of the patient's eye, for example, lens thickness, the anterior chamber depth, or the horizontal white to white. We continue part 1, that is focus on keratometry. The importance of the keratometry is well brought out in this formula, which is the SRK formula, which was introduced in late 70s, very early 80s. The SRK formula states that power is equal to A constant minus 2.5 into axial length minus 0.9 into keratometry reading. That is the average corneal power of the patient. So you can well understand the importance of keratometry in the final IOL power calculation. If the keratometry is off by 1 diopter, then the final IOL power that will be calculated will also be off by 1 diopter, which is well brought out in this equation, right? So in this example, we are trying to understand, taking the old SRK formula, power is equal to A constant minus 2.5 axial length minus 0.9 K. We are trying to understand through this SRK formula, what is the importance of a proper corneal reading, right? So the patient here has 44 diopter of average corneal power, and his axial length 23.5, anterior chamber depth 3.0, and 119 is the A constant. The calculated IOL power is 20.76. Now let us try to see and understand what happens if we are off or we make an error of 1 diopter in the corneal reading calculation. So the patient here is off by 1 diopter. The actual patient's corneal reading was 44 diopters, but we wrongly measured it as 45 diopters. Other parameters remains the same, that is the axial length, anterior chamber depth, and the A constant remains the same. We calculate the IOL power, and now the IOL power is 19.68. So there is a difference of more than 1 diopter when we are wrong in our corneal reading by one diopter. So in other words, to put it, for every one diopter of error in corneal reading calculation, corneal reading, the calculation of IOL power will be off by more than one diopter, as per the SRK formula. So now that we understand the importance of keratometry readings, let us try to understand what is keratometry in theory. Now, you may have seen the biometry output pages, which tells you that the corneal reading in diopters, which shows you the corneal reading in diopters. But what is important to understand is that a keratometer does not measure in diopter. What it measures is the radius of curvature of the cornea. What is the radius of curvature? The radius of curvature, if you take this as a circle, as a sphere, then this is basically the radius of curvature. The cornea is taken as part of the sphere and its radius of curvature is calculated first. From the radius of curvature, the dioptric value of the cornea is then calculated by a formula called D is equal to n minus 1 by R, where R is the radius of curvature that has been determined by the keratometer, and N is the refractive index of the cornea. N is therefore the conversion factor by which the keratometer converts the radius of curvature into diopter. So dioptric value of the cornea is equal to radius of curvature minus 1, which is the refractive index of air, divided by the radius of curvature of the cornea that the keratometer machine has found out. Another important point to talk about is that, remember, flatter corneas have larger radius of curvature. On the other hand, steeper corneas have smaller radius of curvature. So larger the radius of curvature, the cornea is flatter. Smaller the radius of curvature, the cornea is steeper and its dioptric value of the cornea will be more. So dioptric value of the cornea is inversely proportional to the radius of curvature of the cornea. Smaller the radius of curvature, more the steep the cornea is, and therefore the dioptric value of the cornea will be higher, and vice versa. Let us see this image. Here there are two circles, one a bigger circle, the other a smaller circle. Of which circle the radius of curvature will be more? Well, definitely the radius of curvature will be more in the higher, the bigger circle, right? But you can see when the radius of curvature is more, the bigger circle has a flat curve, a flat portion over here. If you have to think of this as a cornea, so the larger the radius of curvature, flatter the cornea will be. Smaller the circle, smaller the radius of curvature, steeper it will be. So a smaller cornea, as a steeper cornea will be associated with a lower radius of curvature. In the last slide, we discussed about that all keratometers first measures radius of curvature and then converts it back to diopters. So all keratometers will throw a light on the anterior corneal surface and then it will study the reflections of those lights to understand the radius of curvature of the cornea. For example, in this picture, light is thrown onto the patient's cornea and the reflection of that light from the anterior cornea is being studied. The radius of curvature is equal to 2 into d, which is the distance from the keratometer to the patient's anterior cornea, into y, which is the image height of those reflections, divided by h, which is the object height of those lights that are being thrown onto the cornea. So radius of curvature is 2 into d into y divided by h, where d is the distance, again d is the distance between the cornea and the keratometer, y is the height of the reflections of the images from the cornea, and h is the height of the reflections or the light that is being thrown onto the cornea. So that is the object height. Y is the image height and d is the distance. So radius of curvature is 2 into d into y divided by h. In this picture, what you see is the reflection from an optical biometry machine. This optical biometry machine, the IOLMaster 500, threw a series of lights on the anterior cornea, and the reflection of these lights were studied and the radius of curvature were determined. The closer these lights would be to each other, a steeper cornea will be indicated. More these lights are farther away from the cornea, the reflections are farther away, a flatter cornea will be reflected. So these lights are nothing but reflections from the anterior cornea, or also we can say as Purkinje's reflexes. So what you see here is what different machines, different keratometry machines, optical biometry keratometers, they measure different areas of the cornea. The Lenster measures 1.6 millimeters and 2.3 millimeters of the cornea. Likewise, the IOLMaster measures around 2.5 millimeters of the cornea. Sorry, this would be 2.5 millimeters. The ALScan measures another different diameter of the cornea. So you may have noticed that the same patient being measured in different keratometers gives us different readings. And one of the reasons why this is so is because different machines measure different diameters of the cornea. The ring diameter that they measure is different. Another important reason why a patient measured in two different keratometers will have two different values is because, remember, the keratometer measures radius of curvature and then converts it back into diopters. In converting the radius of curvature to the diopters, they also take the keratometry index value, which is the conversion factor. This conversion factor may be different for different machines. So you may find a difference of around 0.2 to 0.3 diopters difference in corneal readings for the same patient measured in two different machines. Well, in the last slide, we saw that how the patient's cornea being measured in two different keratometers could give two different readings because the diameter that has been measured in these two keratometers is different. This slide from Jack Holladay explains us this more in detail. On an average, the patient's cornea is prolate in shape. That is, the patient has a steeper cornea in the middle, in the center, and a flatter cornea as we go into the periphery. When a manual keratometer is used to measure the cornea, it measures around a ring of 3.2 to 3.0 millimeters of the cornea. With optical biometry, we are measuring closer towards the corneal vertex. That is, as we measure smaller rings of the cornea and we measure closer to the corneal vertex, chances are that we will end up with more steeper values of the same cornea because now we are measuring towards the center of the cornea, which is more prolate in shape, therefore which is more steeper in shape, right? So the closer we measure towards the corneal vertex, chances are that we land up with more steeper values. As a result, optical biometry in optical biometry, when we move from manual keratometry to optical biometry, the A constant is higher and it takes around zero point 0.2 to zero point 0.3 higher A constants to offset the steeper cornea that we measure with optical biometry. Remember that the keratometer cannot tell you whether the patient has irregular astigmatism. All keratometers will assume that the patient has regular astigmatism. That is, the difference in K1 and K2 values are 90 degrees apart. So, it would be very important for us to see whether the keratometry readings of the two eyes is different by more than one diopters. Here, for example, you can see that the keratometry reading of the two eyes differs by more than one diopter. In the right eye, the cylinder is 1.78, and the left eye, the cylinder is 0.23, almost no cylinder at all. What accounts for this difference? It is very important that the biometrician brings this attention to the doctor, because without understanding that there is a big difference in keratometry reading between the two eyes, the doctor may actually go ahead and implant a toric lens. But there is a clear indication that this astigmatism in the right eye could be because of irregular astigmatism or dry eyes. So the fundamental aspect of keratometry is that you should always see whether there is a cylindrical difference of more than one diopter in two eyes. If so, a topography may be needed to be done, or dry eyes needs to be ruled out. Talking about dry eyes, this example that is given by William Trattler is very important. On the left, you can see that the patient has 1.55 diopter of cylinder, right? And this may call for a toric lens. You may want to go ahead to implant a T4 lens, typically in these patients. But a dry eye was identified, and when the patient went through a 1 month of dry eye treatment and then did a topography, the patient had almost no cylinder at all. So you can see that for this patient, the entire cylinder was actually not because of the astigmatism, but because of the dry eyes. And the patient could have had very bad refractive outcomes should a toric lens had been implanted in the patient without identifying dry eye. So dry eye remains a concern, and it needs to be ruled out before a toric lens is being proposed for the patient when a biometry has been done and an astigmatism has been identified for the patient. So here are basically a few keratometry pearls that we should follow in order to have a perfect keratometry for the patient. Remember that the average keratometry readings are between 43 to 44 diopters, and that if the patient has less than 40 diopters of keratometry reading or more than 47 diopters, that actually indicates that the patient's cornea is too flat or too steep respectively. So it is very important to do the keratometry again to rule out dry eyes, or to do a topography if the keratometry readings of the patient is less than 40 diopters or more than 47 or 48 diopters. When comparing the fellow eye, keratometry readings and corneal cylinder should be within one diopter, and this is something that has been already explained. Remember, a keratometer cannot tell you whether the patient has an irregular astigmatism. So it will always give you a keratometry reading of K1 and K2 values, which are 90-degree apart, indicating regular astigmatism. But it is very important to understand whether this patient has regular astigmatism if there is a cylinder difference of more than one diopter between the two eyes. So therefore, a topography may be called for. So a one diopter of K reading error, remember we discussed this before, can lead to a one diopter of IOL power error. So that is why keratometry has to be done again and re-verified if there is a difference between the two eyes of more than one diopters. If the patient is wearing contact lenses, it is important that this contact lenses is discontinued for at least 8 weeks in cases of hard contact lenses, and soft contact lenses may be at least 4 weeks. And another aspect which is very important is we should never put any drops before keratometry. If we put drops and then do the keratometry, then the corneal curvature changes, which is not the true corneal curvature of the patient. So never put a drop on the eye before doing the keratometry. For optical biometry machines, the axial length calculation and the keratometry reading is done at the same time. It is very important also for optical biometry, during optical biometry, to keep this in mind that we should never put any drop before the optical biometry is done. For accounts where there's no optical biometry and they do a keratometry and then an A scan, ultrasound A scan, it is important to do the keratometry first and then do the ultrasound A scan, because during ultrasound A scan you may be putting drops on the patient's cornea. So it is very important to first do the keratometry and then do the A scan readings.